Hello, everyone. Welcome to pre-lecture 10. This is going to be starting chapter 13 for us, looking at chemical equilibrium. Okay. And so thus far in chemistry, both Gen Chem 2 and Gen Chem 1, by and large, all the reactions we've looked at have just an arrow going from our reactants to our products. These are what we would consider irreversible reactions. However, many reactions are in fact reversible, meaning that they can go both directions with the reactants and products being in equilibrium. And we would designate that with our equilibrium arrow here, where we have one going one way, one going the other. Okay, this is an example here, of course, that we actually covered last class, where we have N2O4 going to 2NO2. Okay. And so the relative concentrations of our reactants and products might vary greatly. Just because something is in equilibrium does not mean, for example, that we don't get a lot of products. We'll talk about how we quantify that a little bit later this video. But basically, something being in equilibrium doesn't mean there are a lot of products or a lot of reactants. It could mean either. Okay. And so I want to contrast this with our last unit of kinetics. And so a reminder that in chapter 12, when we're thinking about the kinetics or the rate of reaction, we're thinking about how fast it goes. We contrast that with what we're talking about in this chapter, chapter 13, we're trying to answer the question, how much of our products and reactants will we end up with? And that is described as a dynamic equilibrium. Okay. And so what we mean in terms of dynamic equilibrium is when we reach a dynamic equilibrium, the rates of our forward reaction and our reverse reaction will be equal. So for example, we have these two things here. And so over time, basically once our concentrations do not change, we are still interconverting between our reactants and our products. But we would say that their rates are equal. So this graph on the left here shows their concentrations. This graph on the right here shows their rates. Again, if we look at our y-axis. And so once our concentrations become equal, or not equal rather, but when they do not change, that is when our rates of our forward and reverse reaction will also be equal. Okay, and that is how we define equilibrium. So in addition to chemical reactions, this can also apply to phase transitions. And so if you think of how we define vapor pressure, it is when equilibrium, the pressure at which equilibrium is reached between our gas and our solid phase. And so here we have an ampule of bromine, both liquid bromine, gaseous bromine that are in equilibrium. Okay, and so that's the chemical reaction. We would still describe this in equilibrium, despite it being a physical change as opposed to a chemical one. Okay, and this being Gen Chem 2, we of course want to quantify this relationship. And so we can do this using our reaction quotient, which we designate as Q. And so our mantra for this chapter and most of the rest of the semester is that our reaction quotient or equilibrium is going to be described by the concentrations of our products over our reactants raised to the stoichiometric coefficients that are present in the chemical equation. So for example, lowercase c here is going to be our exponent there, lowercase d there would be our exponent there. And we take our products over our reactants to give us Q. Okay. So this can be done with concentrations. It can also be done with partial pressures. And so you may see both, but both of those are equally valid expressions. And for reasons beyond the scope of this course, Q will always be unitless. Okay, so this expression will actually never have units. And so this numerical value Q describes the quantities of products and reactants before equilibrium is reached. Okay, so that's a key point here, is that Q is only used when we are not at equilibrium, only when we are not under equilibrium conditions. And so, for example, basically before we reach this dotted line here, we would be in Q. So at the start of this reaction, when our products are close to zero, basically this yellow line here is close to zero, Q would be close to zero. If we started with almost none of our reactants, then Q would be close to infinity. However, once we reach this dotted line, once we reach equilibrium, then Q becomes K. And so these are calculated the same way. It's still products over reactants raised to some power of their stoichiometric coefficients, but K is just the same thing as Q, but now at our equilibrium conditions, okay? And since K is expressed also as a fraction of products over reactants, larger K values will indicate that a reaction has more products than reactants, whereas if we have K values less than 1, that would indicate we have more reactants than products. Okay, that's a very important point. So if you didn't get that, rewind this video, listen to it again. Okay, so if we think about actual chemical equilibria here, we can have homogeneous equilibria in which everything is in the same state. For example, here we have 2 reactants and 1 product. We'd put our products over our reactants. Because we have a 2 in front of our bromine here, we would of course raise that to the power of 2 because of our stoichiometric coefficient. Same thing here, this time with gases. And so we can measure our equilibrium constant either in concentration, in molarity here, or in partial pressures here, okay? I will note that we do have our exponents in both places, right? We can also interconvert between Kp and Kc. So the P there being pressure, the C there being concentration by using this formula, essentially just the gas constant and the change in the number of moles. The change in number of moles there is the change in molar amounts between product and reactant gases. And so, for example, in this one, we have 4 moles of gas on our reactant side. We only have 2 moles on our product side. So delta N there would be 2, okay? Right, we can also have heterogeneous equilibria in which the reactants and products will be present in different phases. A key point here is that pure liquids and solids are not counted as part of equilibrium expressions, okay? The reasons for that is beyond the scope of this class, but essentially you wouldn't have to include this PbCl2 because it is a solid, same with calcium carbonate, same with carbon, same with bromine here, okay? We would not count those in the equilibrium expressions that are shown on the right because they are not a part of the equilibrium, they're not a part of the equilibrium expression because they are solids or liquids, okay? That's it for now. I hope that was informative. If you do have questions, please come ready to ask them in class, and I will see you then. Take care.